Hello everyone, I'm Anubhab, and in this video we are going to talk about extracting biosynthetic pathways automatically from images in scientific literature. Biosynthetic pathway diagrams can often be found in scientific papers studying how certain chemicals are synthesized by enzymes inside biological systems. They are often multi-step and may feature several branches, as you can see in this image. Our goal is to take this image here and automatically extract semantic information from it. We are building Pyami image to do just that. With Pyami image, you will be able to deconstruct an image, extract semantic information, and encode it in a structured format using XML. Using the structured data, you can reconstruct the image in SVG for viewing or perhaps store it as CML. What you see here is an image in PNG format, which means these are just black and white pixels. You can't even copy the text. Now comes Tesseract. For those unfamiliar with Tesseract, it is an open source OCR engine. OCR stands for Optical Character Recognition. On running Tesseract on the image, we get an HTML output, which provides us the recognized words and its location in image with bounding boxes. The entire image has been reconstructed in SVG. We see that we have detected separate words. It worked pretty well detecting the words. It doesn't like graphic primitives though, such as arrows, and it doesn't know what to do with them, as you can see here. But that's not a problem, as we'll deal with the arrows separately. Once we have the words, we can join words which are likely to be together based on their location to form phrases. We use Pyami image to extract a list of such possible phrases from the image. We looked up the detected phrases in databases such as Wikidata, KEGG, and PubChem and annotated it to the SVG. As it is possible to add links to SVG, we convert the phrases which has hits in the database into clickable links. Arrows are very useful because it provides context in its locality. Arrows are abundant in the world of chemistry and chemical diagrams. And universally, they follow a known convention. The tail of an arrow sits close to the substrate or reactant. The head of the arrow points to the product of the chemical reaction. And there is usually annotations perpendicular to the arrow shaft, which may include a variety of information such as reaction conditions, catalysts, and in our case, enzymes, which act on the substrate to give the product. Arrows are our marker for chemical reactions in the biosynthetic pathway diagrams. To detect the arrows, we do basic image processing with scikit-image. And to detect the nodes and edges, we use the skNW library. We use this information to detect the arrows separately in the image. This also gives us the location of the arrow tails, arrow heads, and the path of the arrow. Now we merge the arrows in the SVG to complete the diagram. Let me quickly show you the SVG. Unlike the image we started with, we can copy the text in the image. And hovering over the arrows give us context. And finally, clicking on the chemical names will take us to the relevant database entry. Let's try another one. As you can see, that we are in the KEGG entry for enzyme 1.1.1. So that is the EC number 1.1.1.1. Thank you for listening. If you'd like to know more or get involved, you can find the relevant code and resources on our GitHub repository, that is petermr/pyamiimage. Feel free to reach out to me on GitHub at AnubC. Shout out to my team members at CEV Open for being super helpful. And finally, many thanks to my mentors, Dr. Peter Murray Rust and Dr. Gitanjali Yadav, for their constant support. Thank you.